In this lesson, we'll be working on building the sidewalks and pavers. We'll do this in two sections. First on the exterior, the outside edge of the curbs that go around our roads. And second, for the inner curbs wrapping around the interiors of our city blocks. We can't use the original curves, directly the ones we had before joining, because after joining them, we already unified the curve tangents and offset the exterior boundary. So now we need to separate them again at this point. I'll slide the fillet curve and fill curve nodes over to give us more room. From our offset curve, I'll drag out and add a separate geometry, a node. We'll separate by spline, and for the selection, we'll use the outside Boolean named attribute. This gives us a selection for the outer curve, and its inverse selection gives us the inner curves. We'll begin with the outer one. I'll drag from the selection output, add a reroute, move it up and add another reroute, and finally a third one. Then I'll press Ctrl-G to put it into a new node group. We'll rename the group's input and output sockets. The output will be a mesh, and the input will be a curve. I'll press Tab to exit the group. This node group will be called Sidewalks and Pavers. You'll notice I'm starting the name with a period. That's because when I go to the Add menu under Group, you'll see our utility groups. But the Sidewalks and Pavers, a group doesn't appear. If I remove the period, then it shows up. We don't actually need the Sidewalks and Pavers group to show up in the group menu. It's not going to be used like a utility node group that we'll reuse across different places. We're just keeping it as a group to help keep our node layout tidy and organized. So let's go back into the group. I'll preview the reroute output. What we're going to do inside this group is convert the curve into a mesh and basically skin it using a profile curve, similar to how you would in Object Mode using a regular curve object. When we add a curve to mesh node, up until now I've been adding nodes by going through the Add menu, navigating to Curve Operations, Curve to Mesh, or through Geometry Operations, Separate Geometry, etc. Or I've been typing into the search bar. When using the search bar, you can of course just type in the full node name, like Curve to Mesh. But there's a faster way too. You can just type the first letter of each word. For example, Curve to Mesh becomes CTM, and that will bring it up right away. Same thing for other nodes. Mesh to curve is MTC. Mesh to points is MTP. Instance on points is IOP. And so on. It's just a small trick to speed things up. Now let's convert our input curve to a mesh using the Curve to Mesh node. So, Curve to Mesh CTM, let's add that node. You'll notice it has an input for a profile curve. We're going to build our own profile using a mesh and turn it into a solid shape. Start by adding a grid. Node. I'll hold Shift and Control and click it to preview. We don't need this to be 3 by 3, so I'll set the resolution to 2. Now we decide how big we want the profile to be. This shape will become our paver that wraps around the edge of the road and separates the road from the sidewalk. You could choose to parameterize it by exposing the size inputs to the group, but I'm just going to type the values directly. I'll set the X and Y sizes to 0.2 and 0.1. That should work fine. Next, we need to delete one of the edges from the grid. We don't want the underside face on our paver. It's just unnecessary geometry under the road that won't be visible. To remove it, we'll use a delete geometry node, and we want to delete based on an edge index. For that, we'll bring in the index node. I'll mute the delete geometry node for a moment by pressing M. And we can see that the index node gives us numbers directly from the geometry spreadsheet. Then we drag off from the index output and use an equal comparison. Feed that into the selection input of the delete geometry node. That way, we can delete the specific edge by selecting the right index. We'll delete the one we know needs to go. Next, we need to turn this into a curve, because the profile for curve to mesh must be a curve. So let's use the MTC node, a mesh to curve. After that, I'll also add a fillet curve node to give a bit of smoothness on the corner. We don't need a high segment count here. Setting the count to 3 should be enough. Then I'll set the radius to 0.04, which gives us a subtle bevel. That should be good. I'll remove the viewer node and plug this curve into the profile curve input of our curve to mesh node. Let's also check our outputs. Here's a useful tip. If you press Alt and middle mouse click, it'll center the viewport around wherever your mouse is pointing. This makes navigation a lot easier. So if I'm zoomed in somewhere and want to quickly refocus, I can just press Alt middle click and it recenters the view based on that area. Looking at what we have now, the curve has been skinned correctly. However, we're still getting a sharp edge, so we'll need to add some rounding, just like we did for the road mesh earlier. Previously, we used a segment count of 12 and a radius of 4. Since we said we'll eventually make this procedural, for now I'll just duplicate the fillet curve node and insert it right before the final curve. Set the count to 12 and radius to 4. Now we've added the fillet to this curve as well. Finally, let's join this with our road mesh. We'll use a join geometry node and connect the output of the sidewalks and pavers profile into the main geometry output. Now that we've added that bit of geometry at the edge of the road, let's frame it to keep everything organized. I'll select all the nodes starting from the grid to the final output of the filleted curve and press Ctrl J to frame them. This group will represent our paver profile. Let's also increase the label size so it's easier to see. After that, I'll scroll down in the node layout, because the next step is to assign a basic material. First, I'll delete the reroute node we no longer need. That will make it easier to see what we're doing. We're going to need to UV unwrap this paver mesh. And doing that inside geometry, nodes can be a bit tricky. So I'll open a new window and switch it to the shader editor. Later in the course, we'll set up proper materials. But for now, we'll just create a placeholder material. I'll add a new material and call it road, and set its color to a neutral gray. Then I'll create another material named Pavers. Now I'll add a brick texture node and connect its output to the base color input. Whenever you're assigning materials to procedurally generated geometry in geometry nodes, you have to use a set material node. So I'll drop a set material node onto our road mesh output and assign the road material there. Then I'll go back inside the Sidewalks and Pavers group and insert another set material node. This one will be assigned to the Pavers material. When we switch over to Eevee, you'll see what this looks like. At first, the brick pattern looks kind of stretched. So let's scale it up so we can better see what's happening. This is the direction we're aiming for a tiling brick pattern following the paver path. But as we reach the corner, things no longer look right. This is not the kind of result we want. What we really need is for the brick pattern to follow the path around the road edge. To do that, we need to UV unwrap the mesh. There is a UV unwrap node, but it won't produce the result we're after. Just like if you UV unwrapping this in edit mode, it won't lay out the UV in a straight line. So, we'll need to build that mapping ourselves using attributes. If we check the mesh data and look under attributes, we'll notice that there's already a UV map attribute created by default. That's because when you add a primitive mesh in Blender, it comes with built-in UV that exist as 2D vector attributes on the face corner domain. So right after converting the curve to a mesh, we'll use the store named attribute node to create our own UV map. We'll set the domain to face corner, the data type to vector 2D, and name it UV map. If I click the drop-down, you can see that this name already exists because Blender has it pre-generated. So now let's define the values we want to store. First, we need a combine XYZ node. Connect that to the value input. This gives us control over the X and Y inputs. We won't need the Z value. To drive the UV coordinates, we'll use the curve length. This will let us control how stretched or tiled the bricks appear across the surface. When we're working with curve lengths, there are a few different nodes we can use, and each one behaves differently. So let's search for a length. You'll see two nodes show up: curve length and spline length. I'll add both of them for now so we can compare. We'll focus on our paver profile, so let's preview that. I'll recenter the cursor and zoom in. First, the curve length. Node requires a curve input. Let's connect it and preview the result. This gives us the total length of the entire curve. However, that might not be what we want. It's not obvious here because we only have a single spline. But just to demonstrate the difference, I'll add a curve line and join it with our profile curve using a join geometry node. Now that we've joined two curves together, we have two splines in the same geometry. The curve length node is returning the total combined length of both splines. This is not going to work for our needs, especially when we get to the interior sidewalks, where we might have 4 or more splines in a single input. So this method won't help us. I'll delete the join geometry and the extra curve line. Now let's try the spline length node. I'll reconnect it to the original profile and preview the output. This gives us a single value per spline, which is already better. But it still doesn't give us data per point. We need more precision. What we actually want is the spline parameter node. And if we look at the length here, now we get a gradient or range going from 0 all the way to our total spline one. So this is what we're going to use to create a UV map. So we're going to use another capture attribute node. And we're going to capture the spline parameter length on both the profile curve and on our main curve. So that's all. And we can then just hook these up to the X and the Y inputs of our UV map. We need to hook up the attribute into our brick texture. So I'm going to add an attribute node in the shader editor called UV map. Take the vector and plug it into our brick texture. We now need to make this a lot smaller. Now that is what we want, where our bricks are continually following around the curve profile. There is, however, one problem with this. If we look here, everything else looks perfectly fine. But this edge here is all squashed. And that's because our curve is a cyclical curve. And what's happening is that the length is going all the way around here. But when it gets to the end, at the end of our curve, here, it doesn't know how to interpret that edge here. Instead, the UV map is getting to this point, and then wrapping all the way back around to the start. So what we need to do is actually manipulate our curve so that it is, in essence, a spiral. We need to break our curve at this point. To do this, we're going to use one of our utility node groups, or rather, we're going to create one again. This one will be called curve to spiral. So let's add a reroute, and then press Ctrl G. Just like we've done previously, to group this into a new node group. This node group will have a curve input and a curve output. Let's rename both inputs and outputs accordingly. Then I'll rename the node group itself to curve to spiral. The method we'll use here is similar to what we've done several times before we'll convert the curve into a mesh. Modify it, and then convert it back into a curve. The first thing we need to do is change the spline from cyclic to non-cyclic. If you open the spreadsheet view and inspect the spline, you'll notice there's a cyclic attribute, and it's currently set to true. There's a node called setSplineCyclic that allows us to toggle this. So I'll drop that into the group. We'll disable the cyclic toggle by setting it to false. That effectively breaks the curve at one point. Now, let's convert the curve to a mesh using a curve to mesh CTM node. After that, we'll extrude the final vertex all the way back to the original position. We're going to use the extrude mesh node for that. We don't want to extrude any faces, just the vertices. And you'll see we've got an offset scale input here. Problem is this is extruding all of our vertices. But we only want to extrude the endpoint. Luckily, for curves, there's a node called endpoint selection. So let's bring back our curve into view and zoom in to see it better. As I adjust the start size and end size, you'll see we're getting a Boolean value. The white ones are true, and the black ones are false. If I set the start size to 0 and end size to 1, we'll get false for all points except the final one, which will be true. Now, the question is, how do we pass this endpoint selection from the curve into the mesh domain of the extrude mesh node? Because plugging it in directly won't work, the domains don't match. This Boolean lives on a curve, and we need it on the mesh. So we're going to use a capture attribute node. This is one of the useful features of capture. Attribute it lets you carry data from one domain to another. We'll capture the selection on the curve, convert to mesh, and then use that captured value as the selection input for extrude mesh. Now, we're only extruding the final endpoint. We can now set the offset scale to 0, since we're not trying to displace anything yet. What we want to do is to set that position back to the stop point. So let's use a set position node. And using the offset input, we'll control where that extruded vertex goes. But we don't want to offset all the geometry, only the part we just extruded. Fortunately, the extrude mesh node gives us a built-in selection for that. It's the top selection output. So we'll take that and plug it into the selection input of set position. Now, when we move the offset value, we're only affecting the extruded geometry. Next, we need to determine exactly where we want to move it. We're going to snap the extruded point back to the position of the original start point, index 0. So, how do we get the position of index 0 from the mesh? Let's drag off from the mesh output and add a sample index node. The sample index node allows us to extract any data type from any domain at any index. We could give it an index input that varies, but in our case, we only need index 0. So, in the index field, we'll enter 0. Now, what value do we want to sample? We want the position. So we set the data type to vector and select position as the attribute. Then we plug the result into the offset input of the set position node. We now snap that back to the end. So if we come out of this and we look at our mesh, it's not working right now because we need to convert this back to a curve from the mesh. So we'll add a mesh to curve node MTC. There we go. Now we have the correct output. These are not squashed and are shaped how we want them. The final issue we need to fix is that because we've now converted these to a spiral and broken that geometry, this section here is no longer connected. It's split, and because it's slightly out of bounds, we're getting these weird angles, and we can see a visible gap in the geometry, which is of course not what we want. So we need to merge these back together. Before I do that, I'm going to group up or frame these nodes that relate to the paver, UV. We'll select them, frame them, and increase the label size. Now, we'll fix the disconnection. Let's add a merge by distance node. This works just like the merge by distance tool in edit mode. If we start increasing the distance value, we'll see that the geometry begins to merge. How much should we set the distance to? We don't want to break the fillet curve, so let's set it to 0.02, which is half the radius we used earlier. That looks accurate and seems to work well. There is going to be an issue with this later on, when we do the interiors, specifically the interior curb for our sidewalks. But we'll handle that when we get to it. Finally, all we want to do is to take all of these and duplicate them for our sidewalks. But we'll do that in the next lesson.